Hi, this is Wayne Schaefer coming to you from my basement workshop again. I want to show you a project that I've been working on for one of my colleagues who also teaches PLC programming and control systems. My intention is to always show or demonstrate how an approximated simulation can be used to complement a student's experience by providing a risk-free and therefore also a reduced stress environment to practice on before attempting to control a real physical device. Simulation can also be used to reduce the need and therefore the cost of building and maintaining a large number of mechanical or electrical trainers. In the example I'm going to show you, I would estimate about 80% of the programming techniques used to get the simulated apparatus to work would also translate directly to the real machine. Unfortunately, I can't show you a copy of the system at this time due to restrictions of trying to get back into the lab, but let's take a look and see what I've come up with over here.
What I have here is a simulation of the conveyor system we built in one of the labs. A stack of colored blocks is loaded into a tube at the start of the belt. At the bottom of this tube is a color sensor. The sensor sends a signal to the PLC based on the color of the block at the bottom of the stack. Once the color has been determined, a pneumatic cylinder is used to push the block forward onto the conveyor. The motor is then turned on and the block is transported by the belt. One of the 3 cylinders is then used to push the block into the bin designated for that color. If the color is not determined or is invalid, the block would then continue until reaching the end of the conveyor, at which point it is deposited into a reject bin. Once a block has either been unloaded into one of the 3 bins or rejected, the cycle can be repeated. Processing one block at a time helps keep the programming at a fairly basic level. The actual conveyor system doesn't quite have everything shown here, such as individual part-present proximity switches, but it does have a proximity switch that pulses twice for every rotation of the drive sprocket. This can be used to determine the position of the block as it travels along the conveyor. Now, you may have noticed something strange about my recovery bins here. Non-movable objects cannot occupy the same space as other objects in the simulation. This is also true for movable objects such as boxes, bins, pallets, and machinable material. The emitters and removers are unique in that, during run mode, movable objects can pass in and out of their boundaries. However, this is only true in run mode. For my conveyor setup, I did not want the colored parts to begin dissolving until they actually dropped into the storage box. So I placed the box on top of the remover at build, and this way it will drop into position at run mode, like this. The removers are set to ignore the stackable boxes, so this way they can act as bins because only the parts falling into them are actually removed. Now the beams on the floor prevent the box from being pushed out of position by the parts falling into them. So let's go ahead and start this thing up, and I've given you a window view of the panel so you can see what I'm doing. First of all, we have to adjust the speed and turn on the conveyor, and we're going to leave the setting to use the part present sensor instead of the encoder to locate the part. I've left the encoder count displayed on the screen so you can see the position the belt stops at for each of the colors. And this turns out to be about 71 for blue. And you're going to see 112 for the metal and 32 for the green. I mentioned the conveyor speed adjustment before. We'll come back to that later. For now, I've adjusted the speed so that whether we use the encoder or part present, it doesn't have any major effect on where the part stops. And we're going to switch to an overhead view. The overhead view shows that the belt stops distance about a quarter way down the width of the part. The time to stop is a combination of the processing time, communication time, and the 100 millisecond debounce timer I've added in the logic. Again, like I said, I've chosen the belt speed that minimizes any negative effect caused by selecting either part present or the encoder, so they'll stop in approximately the same place, and you're going to see that in a minute for the encoder. Now I'm going to show you a similar sequence. However, as an alternative, we're going to select Use Encoder. Then we're going to adjust the speed similar to what it was in the previous example. And then we're going to turn on the conveyor. In this mode, once the part color is determined, the target position is displayed and the PLC uses this value as the stop point. Now, because of some delays in the system, the belt could actually stop a bit after the set point, so I've actually created a stop window of basically the set point plus or minus 2. I think this is a good representation of our lab conveyor, with the added bonus now of being able to add and experiment with part present sensors. You can see the target there was 112 and it actually stopped at 112, so it was pretty good there. Again, as you can see by the overhead view, the part stopped relatively in the same place. I turned off the indicator that shows where the part present switch is sensing, just kind of to drive home the point that this is using the encoder. In the next video, I will show what happens when the conveyor speed is fast enough to become a significant factor as to where the part stops. But to keep this short, we'll stop here, and as always, thanks for watching.